Welcome to Astronomy, second semester. This is going to talk about the solar system, just a general overview of the solar system. And their homework is that. You saw that in class, hopefully. The solar system, we talk about comparative planetology, which is basically what it says, comparing planets, their similarities and differences, and what we know from what experiments we've done here on Earth to figure out what the planets are made up of, their size, their mass, their density, all that stuff. So helps us better understand them. Solar system components. There are some things in the solar system. Obviously, our star, the sun, is the center of the solar system, and there are 8 major planets, which means there are 8 major bodies orbiting the sun with 166 plus, more than that now, natural satellites that we know of orbiting them. Now, our natural satellite is the moon around Earth. There are 7,000, greater than 7,000 asteroids that have been well studied. The biggest used to be Ceres. Ceres has been upgraded to a minor planet. It joins Pluto as a minor planet status. Pluto got downsized years ago, and Pluto does have Charon, its little natural satellite orbiting it. There are a lot of comets out there, and most of them are anywhere from a half mile to 5 miles in diameter. It's pretty big. Comets are unique in that they're big, dirty ice balls that basically have a very elliptical orbit. That means it's more ovoid than circular, and they graze the sun. They come pretty close to the sun within 1 AU, or 1 astronomical unit, which is the average distance the Earth is from the sun. And then they go out there for a long time. Like our most famous one is the 76-year comet Halley, and Halley won't be back to like 2050 something. But it goes really close to the sun. And the solar winds blow the tail away, and you can see that. But there's also a lot of meteoroids, anything from dust grains up to a football field in size, which is 100-meter basically diameter. They call a meteoroid. Now, when meteoroids burn up in the atmosphere that short time, we call that a meteor, shooting star. It's the shortest word of the three: meteoroid, meteor, and meteorite. Meteorite is if that meteoroid should make it all the way to the surface of the Earth and land right on the Earth. Okay. The solar system, pretty much our knowledge from the ancient Greeks on up, remained almost unchanged. Tycho Brahe, the great Danish astronomer, used just a sextant way long time ago and made amazing observations, which then Johannes Kepler followed up with some math and was able to find out the distances the planets were from the sun in terms of AUs and their orbital periods in years. Pretty amazing work. And then Galileo took a telescope and aimed it and found a lot of stuff, but until recently, there wasn't a whole lot known. So again, the solar system objects: the sun, the 8 planets, the natural satellites, our moon, the asteroids, which are minor planets, and minor planets, and greater than 100 Kuiper belt objects. Kuiper belt is that area outside Pluto, but it still has some solid objects out there orbiting the sun, and those are pretty big. They're greater than 300 kilometers in diameter, which makes them like minor planets. And then there's millions and millions of meteoroids, like I say, anything from dust up to 100, up to 99.99 kilometers. You say, what is it? It's 99.99999 kilometers in diameter. Yeah, we probably call it an asteroid just because it's so big, but that's your dead cut observation, or right there is the definition, is that it's 100 kilometers and a lot of comets. The ancient Greeks, they only recognized some things. They saw the stars, they saw a sun, of course, the moon. The stars they thought were just fixed lights in the heavens. They really didn't know they're big burning balls of gas. The comets, because they'd see those come by. Of course, meteors, because those would burn up in the atmosphere. And then Mercury, Venus, Mars, Jupiter, and Saturn, because you can see those with the naked eye. Back in those days, they didn't have TV, they didn't have electronic items. Yeah, lights. So it was nice and dark skies at night, and a lot of times they just looked at the sky a lot. So they made some great observations. All right. So again, meteoroids are anything in space up to 100 meters in diameter. Meteors are that flash or burning we see through the atmosphere as they're burning up. And if they don't burn up totally and they landed on the Earth, that's called a meteorite. An asteroid is any solid rocky object, basically 100 kilometers or 100 meters in diameter or bigger. And we call the asteroid belt that area between Mars and Jupiter where there's a lot of asteroids. Now, that asteroid belt isn't really like a belt. You think you're going through an asteroid belt, you might hit an asteroid. You're lucky to see an asteroid. They're so spread out. There's so much space out there. And then comets are usually 1 to 10 kilometers in diameter, and they're big, dirty ice balls, basically. Interplanetary debris, all that stuff that blows off, the dust that just kind of hangs out there that can become meteoroids, or well, basically is meteoroids. They just call it interplanetary debris. There's not a whole lot of it, otherwise it impede our view of the stars. It's pretty tenuous or thin, very low density. Since the 90s, though, we've detected a whole lot of exoplanets, extrasolar planets, exo. They just take the X and the so for solar. That's where you get exo as extrasolar, outside of our solar system planets. So the word exo, people think sounds pretty cool, but it's just shortened. But data suggests that many of them have totally different properties from those of our own. The closest we've found of having water, maybe Earth-like, is as big or bigger than Jupiter, they think, and that'd be way too much gravity. Back in about August of 2000, in the journal Science or Nature, these astrophysicists and astrobiologists all got together and published this amazing piece, which basically said chances of having another Earth-like place to live on, which has our atmosphere, our size of gravity, our water, available for carbon life, orbiting a sun, a star, big enough to support life, far enough away not to burn it up, but close enough to give life, and all that. All the stats added up to about 1 in, I don't know, 100 million zeros or something crazy. The chances were almost nil that you could have something just like Earth. But then again, there are a whole lot of galaxies out there. So this is one of my favorite pictures from the 90s. When this came out as my screensaver, they took Hubble and aimed it at a very dark spot, and they just left it there. And after a while, it just kept collecting data, collecting data, collecting data, because out there was no light pollution. And when they finally looked at the image, they saw these thousands of galaxies outside our galaxy. So it's pretty cool. All right, there's what you're going to do in class as homework. We are going to address elementary, and we're going to present the weather and the atmosphere on these other planets, and it's a fun thing we do. There's your topics you pick. Okay, this table's from the book. Basically shows the semi-major axis, or the distance, average distance away from the sun. These planets are, and AU is again is the average distance the Earth is from the sun. That's why Earth is 1 AU. It's 150 million kilometers equals 1 AU. Got to know that. So with that information, some facts about the solar system you got to know is that basically everything kind of goes on like it was put on a turntable. The sun orbits or rotates on its axis in the same direction the planets go around it. The planets are all orbiting roughly the same plane, like they're on the same floor. You can see Pluto is not directly on the same plane. Everything else is pretty flat, but Pluto, it's a little odd. Mercury, Venus, and Jupiter, you can see them in the picture because they're all on the same plane, roughly. We have natural satellites or moons orbit in their respective planets about the same direction as the planets orbit the sun, which would be counterclockwise. Natural satellites, the moons, they rotate in the same direction, most of them, not all. There's always some anomalies. I mean, Uranus rotates on its side, it goes up and down. And Venus goes opposite way in terms of planets, but all the other planets rotate in the same direction. All the orbital paths are elliptical. That means they're not perfect circles. However, they have extremely low eccentricity, which means they all look like circles except for like Pluto and then the further ones out. And the orbits of planets are spaced further out as they progress. You'll heard it called the Titus-Bow law, but it's really the just a Bode progression or Titus-Bode progression, which is a mathematical analysis. So it fits a mathematical scheme. It's pretty cool. Mars has only 2 natural satellites. Earth has 1. Mercury and Venus have none. So the terrestrial planets shown here only have 3 total natural satellites orbiting them. There's over 160 some odd natural satellites orbiting Jupiter, Uranus, Saturn, and Neptune. So comparative planetology, again, is comparing the planets and their properties to understand the conditions under which we think they change and could have formed. Again, here's some planetary properties. These are nice to know. Here they show Haumea, Makemake, and Eris further out of Pluto. You can see Eris is the mean distance from the sun in AUs there is 67.668. That's 67 times further away from the sun than our Earth. Pluto is 39 times further away. It's way out there. How do we know the mass, the size, the weight, the magnetosphere? How do we know so much about planets, the distances to planets, the orbital period? How do we know all this? Because of comparative planetology. Stuff we study here, we take out there, and we can look at like the mass, we can find out its action of gravitational tug it has on natural satellites. We can see how light lenses or bends, as it were. Starlight tends to change as these planets come between us, and then we can find out the actual mass of that planet. It's just a fine science. So here's Bode's, again, they call it Bode's law. It's a progression. It's a mathematical pattern they came up with. It's basically 0 plus 4 divided by 10, 0.4. Then you start doubling, put a 3 on there. 3 plus 4 divided by 10, 0.7. Then double the 3, makes 6 plus 4 is Earth at 1 AU away, which the definition of an astronomical unit is Earth, distance from the sun. Double 6, you get 12. 12 plus 4 divided by 10 is 1.6 is Mars. And this pretty much holds true. As you can see, the asteroid belt falls in the next one. So that would have been a planet except for the tug of war between Jupiter and the sun. The gravitational tug didn't let the asteroid belt all accrete into a planet, is the theory anyway. We weren't really there when it all happened, so we don't know. Saturn, Uranus. Neptune's an anomaly. It doesn't quite fit the progression. Again, Neptune also orbits on its side, so or rotates on its side. It probably got knocked out somewhere by something. And then Pluto and Eris doesn't really fit. So it works for the major planets though, for the most part, except for Neptune. It's pretty crazy. In order to find the mass of a planet, we always take density equals mass divided by volume. By using that, you can run through this as a sample practice question here, which of course you have in your homework, you'll have in class. We'll discuss these in the flipped class concept. This is how you set it up. Density equals mass divided by volume. You take that information, plug it in, and the volume of a sphere is 4/3 pi r cubed. Our planets are spheres. So the volume is 4/3 pi r cubed. You plug it in, and you come up with 366.52 meters. What was the question? What's the diameter? Okay, the diameter is 356